So, good afternoon, students. Actually, here we are going to continue the last concept we have studied in the last video. Actually, we have studied the concept of range space in the last class. So, what is a range space? It is just a set that is T of x such that x belongs to V. We already know this one. So, a dimension of, that means the set is denoted as R of T. Now, a dimension of R of T is called just a rank. Okay. So, what is the rank of T? Rank of T is dimension of R of T. What is the dimension of R of T? Number of elements in a basis of R of T. Okay? That you have to keep it in your mind. Now, we will see the next concept, null space. Null space. So, can we start? Null space is, again, null space of T only. T is linear map. Now we are we are just having a map T V2W. Null space is denoted as N of T, which is equal to N of T, which is equal to a set of all x belongs to V such that T of x equal to 0. What is the local meaning of that? You just tell me. Actually, this meaning of null spaces, you have to collect every elements from a domain. That is, in this map, a domain is V. We have to collect x from V. Those elements are going to 0 in the W. Okay. You have to collect all the elements from V, which is going to particular element 0. Okay, not to all other elements. Okay, this is the set notation. And for example, I am writing a map. That map is T of x comma y comma z equal to x comma x plus y. Okay, this is the map. So, by the definition of n of t, we have to write it as x belongs to V. V is here R3 because these elements are 3 tuples. So, R3. So, you are going to collect 3 tuples elements from V. This V is nothing but R3. Now, and just writing T of x comma y comma z equal to 0. Okay. From this above definition, we have written this one. Next is, we have to apply map. Okay, what is a map? X comma y comma z belongs to R. We are going to collect some x, y, z. But which type of x, y, z we are going to collect? T of x comma y comma z equal to 0. That map should be 0. So, what is your map? X comma x plus y is your map. And by this definition, 0 should be there. So, 0 means here R2. So, you have to equate with 0 comma 0 only. Okay. In the next step, x, y, comma, z equal to 0 is the definition. So, which kind of x's? X, comma, x plus y equal to 0, comma 0. So, component wise, I'm going to equate the elements. X equal to 0, x plus y equal to 0. See here, in this step, x equal to 0, we know that. Okay, x equal to 0 and y equal to minus x. Okay, x equal to minus x. But we already know that x equal to 0, right? So what type of solution we will get here? The type of solution is actually here x, y, z we are having. Map should be in the term of x, y, z. So I'm just writing plus z also. Okay. Here I'm just adding plus z. So likewise here also we have to add z 0 comma 0. And here also we have to add z. Here what can we write is we are going to equate component wise. X equal to 0 is okay. In the next step we have added z, right? So x plus y plus equal to 0. X is already 0, we know that. So we are having y plus z equal to 0. So y equal to minus z. So in this step, we have to minimize the variables. If how much variables you are reducing, it will be reduce your dimension. Okay. The most important thing is minimum set only you have to collect. So I'm going to write x equal to 0. So I already know that x equal to 0. So I'm writing 0 as x, and y equal to minus z. Okay, y equal to minus z. So that means y z equal to minus y. So here we are having y 0, comma y, comma minus y. So these elements. Here y only involved. So y belongs to R. Okay. So this is your null space. So now null space is denoted as n of t. Okay. Null space. So n of t. So here what is the basis of this element? As we found already, we are going to write it as span of, we just take y outside. Y term only here. So 0, comma, second tuple has 1y. So 1y. Third tuple has minus y. So minus 1. Such that y belongs to R. Now, if this format is in the format of alpha 1 v1. So alpha 1, in place of alpha 1 we are having y. In place of v1 we are having 0, 1, minus 1. So the set can be written as a set is 0, comma 1, comma minus 1. Here only one element we are having. Only you just keep it this result in your mind. That result is nothing but any non-zero element, any singleton non-zero element in the set is always linearly independent. So this set is linearly independent. Also, we have derived this from the format of span. So it is span of n of t. Okay. So this concept is tell that s equal to 0, 1, minus 1, which is a basis of, from which set we have derived this set? N of t. From n of t we have derived this s set. So that is a basis of n of t. Okay. Till this you can understand. Now, what is the dimension of null space? You have found the basis of null space. Basis is 0, comma 1, comma minus 1 is a basis. You have found that. Number of elements in a basis is called dimension. So dimension of n of t equal to 1, which is nothing but a nullity. Okay. How we are saying dimension of R of T as rank. Now, dimension of null space is called as nullity of T. Okay. So, this is the concept of null space and range space. Now, I am going to discuss about one theorem that is nothing but dimension theorem. Very important theorem actually this is dimension theorem. This theorem is called dimension theorem. Also, it is known as a rank nullity theorem. Rank nullity theorem. A proof of this nullity theorem, the proof of this theorem is also important, but I am just writing the statement only here. Okay. Let V, W or the vector space or the vector space over field F. T is a map from V to W. Then the rank nullity theorem states that dimension of V is always equal to rank of T plus nullity of, that means rank and nullity of T. How can we write this same statement with another words? Is dimension of V is dimension of V, which is equal to rank is nothing but dimension of range space plus nullity is nothing but dimension of null space, right? So this is the another statement you can use for this theorem. Okay, can we verify this theorem with some other examples? So I'm just writing one example, that is T of x comma y equal to x plus y comma x. This is your map. Just I'm asking you to verify rank nullity theorem. This is the simple question, but we have to find more for this sum. What are all things we have to find is, first we have to find a range space, then the basis of range space, then the dimension of range space. Next, null space. We have to find null space, then a dimension of null space, and finally we have to find a dimension nullity. Okay, dimension of null space is nothing but nullity. So these two things we have to add, and finally we have to check whether it is equal to dimension of P. Okay, first of all, we have only map. This map is going from which vector space to which vector space. First, we have to find that. Okay, what is the map? T is here two tuples. So, R2. 2. Here also two tuples. Okay, that means x plus y is a one tuple, comma x is a one tuple. So, R square, that means R2 goes to R2. So, here no problem in the map. Now, I am going to check the set of R of T. Already we have the definition. What is the definition? T of x such that x belongs to V. For this definition, what we have to write? The set is T of X. X belongs to V, right? So X is nothing but as element from V. V, which is nothing but, V is nothing but R2. W is also R2. So the X, instead of X, I am going to write the element of R2. X comma Y, such that X comma Y belongs to V. Okay. Now in the next step, I am going to write a map. T of X comma Y. In this map, what they have given? X here, X plus Y comma X. They have given X plus Y comma X. So, such that X comma Y belongs to V is nothing but R2. But here X is separately one element, Y is separately one element. So that means X and Y comma belongs to real. That is only we are going to write. Now this is the R of T set. R of T we have find. So range space we have find. Now we have to find a dimension of range space. To find a dimension, we have to find a basis. Why? Number of element in a basis is nothing but dimension. So before going for the dimension, we should know about a basis set of range space. Okay. So basis set is nothing but how we can find a basis set from a span. This R of T can be written as I told, span of, I am going to take a X outside. Now it is nothing but 1 comma 1, because in first component also we are having X. In second component also we are having X. So that's why first component I am taking 1 comma second component also I am taking 1. Plus now I am going to take Y outside. Y is nothing but in first component we are having 1 Y, so that means 1 comma. In second component we don't have any Y, so that's why we are writing here 0. Okay, so see that X comma Y comma belongs to R. Now here again we are having a format of alpha 1 V1 plus alpha 2 V2. So S is V1 comma V2, which is nothing but 1 comma 1. First vector is 1 comma 1. Second vector is 1 comma 0. Okay. So here equal to N of T. Sorry, this is R of T. So R of T equal to S set. Okay. And next we have to check whether it is linearly independent or dependent. The set S is linearly independent or dependent. How can we check? Again, alpha 1 V1 plus alpha 2 V2 equal to 0, we have to substitute. We have to check alpha is a 0 or non-zero. So, alpha 1 V1 is 1 comma 1 plus alpha 2 V2 is 1 comma 0 equal to 0, we have to substitute. Now, alpha 1 plus alpha 2 equals 0. If we simplify, we will get this one. Alpha 1 equal to 0. Now alpha 1 equal to 0. If we substitute alpha 1 equal to 0 in the first equation, alpha 2 equal to 0. Anyway, both the alphas are 0. That's why the set S is linearly independent. Okay. So, first option also second option of base is satisfied. So, first option of basis is also satisfied. So, then we can say that S is a basis of what? Basis of, from R of T we have derived these things. So, basis of R of T. I hope you understand these steps. We can go for the next step. So, basis of R of T is S. So, S set is nothing but 1 comma 1, 1 comma 0. So, what is a dimension? Dimension of R of T, which is equal to rank, which is equal to number of element in a basis. Okay. So these three definitions you can write for the dimension of R of T. Okay. It also known as rank of T. It is also known as number of elements in a basis. Okay. Basis of R of T. These three you have to write. So anyway, number of elements in a basis is 2. So rank equal to what? 2. So rank. Till now we have found rank. Keep it in your mind. Rank is 2. We are going to verify theorem. Before we have to know about N of T. So what is your N of T, pa? N of T is, it has one formula, right? I have given in the first slide. So T of, sorry, not T of X, which is, we are going to collect X's first. X belongs to V such that T of X equal to 0. So map is nothing but first R2 from R2. So set of all X comma Y belongs to R2 such that T of X comma Y equal to 0 comma 0. This is the definition from our map. Now we are going to find the X and Y's which are all satisfying this condition. So T of X is nothing but our map. I have given that last map as X comma X plus Y, right? So X comma X plus Y equal to 0 comma 0. Okay, X, sorry, I have changed the map, I think. X comma X plus Y, yeah? Or X plus Y comma X equal to 0 comma 0. Okay, this is the map I have given. So how we can equate X equal to 0? X plus Y equal to 0. X equal to minus Y. Okay. Anyway, see, listen. Here X equal to 0. If we substitute X equal to 0 here means then Y equal to 0. Anyway, X equal to 0, Y equal to 0. Right? So, finally X should be 0, Y should be 0. Here we are having only 0 element in as a block T. Okay. So, dimension of 0 element is always 0. Okay. Because basis element is empty. Why we are having here 0. Okay, 0 element. 0 element is always linearly dependent. Keep it in your mind. 0 element is always linearly dependent. If it is linearly independent, we can take it for the basis. But there is no element is linearly independent. So it should be linearly dependent. Linearly dependent element should not be placed in basis. So linearly independent element only should be placed in the set of bases. So we don't have any linearly independent element. So basis is empty. So number of element in a basis is 0. So dimension of N of T is here 0. So before itself we have found rank of T equal to 0. Nullity is nothing but dimension of N of T. Okay. That means dimension of N of T equal to 0. Nullity is 0. Now we are going to verify the rank nullity theorem. How can we verify rank nullity theorem? Dimension of V. Dimension of V equal to rank of T plus nullity of T bar. Okay, nullity of T. Here, rank of T, rank of T we have found it as 2, right? Before before slide we have found that rank of T equal to 2. So here rank of T equal to 2 plus 0. Here in the first slide I have written that dimension of V. V is nothing but R2. Dimension of R2 is nothing but 2. So 2 equal to 2. So we have verified with this theorem. Okay. This is the concept of rank nullity theorem. Now, these are all the concepts of rank nullity theorem. And now, the linear transformation can be called as a 1-1 linear transformation, onto linear transformation, and everything. I am just going to write a linear transformation when it will be 1-1, when it will be onto. Linear transformation. 1-1 first. 1-1. If the nullity of T equal to 0. Okay, nullity of T equal to 0, then we can write it as rank of, not rank. Nullity means dimension of range space or null space? Range space. Null space. Okay. So, dimension of n of T equal to 0. That is, basis is empty. Okay. If these three conditions are hold, then we can say that the linear transformation is 1-1. In previous sum also, we have derived that T of x comma y equal to x plus y comma x, right? In this sum, finally we got that nullity equal to 0. So nullity equal to 0 means this condition satisfied. So this map is T of x comma y. The map is called as, what is that? 1-1. That means 1-1. Okay, 1-1 linear transformation. Next, in which case we can say that the map is onto. Usually in real analysis we can say that every element in a domain has a unique element in a codomain. Then that is a 1-1 map. Similarly, this concept is related, and onto map means every element in a codomain should have a preimage, at least one preimage in a domain. Likewise, only here also we are having onto linear transformation. Onto linear transformation. How we can say that onto linear transformation? T of the map is not map. I will tell definition first. If range space of T, which is equal to full W vector space. We know that T is a map from V to W. when we are finding range space, if we are getting that range space equal to this full W, then we can say that the map is onto linear transformation. For example, we can consider last example itself. Last problem I have given is both 1, 1 and on 2. What is the problem? X plus y, comma x. What you have to find? R of t you have to find, right? R of t is nothing but, by the definition, R of t of x such that x belongs to V. Okay. Here V is R2. Here left hand side, the tuples are 2 and right hand side is also tuples of 2. So that's why T is going from R2 to R2. P is also R2, W is also R2. Okay. Now, this is a definition of R of T. T of X is nothing but T of X comma Y such that X comma Y belongs to R. Now, what is your T of X comma Y? The map is X plus Y comma X such that X comma Y belongs to R. So now this X plus Y can be written as alpha 1 comma some alpha comma 2, alpha 2 such that alpha 1 comma alpha 2 belongs to R. Can we write like this? Because alpha 1 can be written as X plus Y. Okay. X plus X is also from real numbers, Y is also from real number. Addition is also will be a real number. That real number I have written as a alpha 1. Okay. Alpha 1 comma alpha 2. This is the general definition of R2. Can you agree? This is the general definition of R2. So, our R of T generated the full W space. W is nothing but R2. So, our R of T given R2 fully. So, this map is onto map. In other words, we can say that rank of T equal to dimension of W. Rank of T is 2 we have found in the last slide, which is equal to R2. Dimension of R2. What is your dimension of R2? Dimension of R2 is 2. Okay, so both are equal. That implies the map is onto. Okay, so this is the very important topic in linear algebra. So you can go through this. In the next concept, we are going to learn about if the map is given, how can you find linear transformation? If the linear transformation is given, how can you find the matrix representation of your map? Okay, simply I will explain. Simply, very simple problem only I am going to explain. So, first of all, we can find a map from a that matrix first. Okay, I am writing one matrix first. What is a matrix is T equal to 1, 2, 3, 1, 0, 1. This matrix represents one map, that is linear map. What is that map? Can find it. How can we find this? Number of columns is 2. Number of columns is 2. So, Tx equal to, T is nothing but 1, 2, 3, 1, 0, 1. So number of columns is 2. So that's why you can write 2 elements in a same column. How can we write this? You just multiply these two matrix. This is a 3 by 2 matrix. This is a 2 by 1 matrix. You can multiply. That means x plus 2y. In next, 3x plus y. Next, 0x plus y. So this is the map. So T of so here the map is this is the 3 by 2 map. While you are finding the map from B to W in the format, we can use column first and row next. That means T is a 3 by 2 matrix. Next, when you are writing real numbers to real number, first you have to write a number of columns in the vector space V power. In the power of W, we can write a number of rows. So, this is the columns. We have swapped the number of rows and columns in the T map. Okay. So, the map, the number of columns is 2. So, firstly, I have written R power 2. Goes to, the number of rows is 3. So, I have written here R power 3. So, what is a map? Now, the map is going from R2. That means x comma y, T of x comma y, which is equal to nothing but what we have derived here. X plus 2y, comma 3x plus y, comma y. So, this is your map. Okay, you can easily calculate this one. I will give some practice problems for you. You can practice by your own. If you are having any doubt, you can comment me. Now, I am giving some problems for you. T equal to 3, 2, 1. It is a matrix 2, 1, 0, 0, 1, 0. This is the matrix. Find T. Find T. This is just nothing but. So, by this problem, we can tell that any matrix can be represented by one map. Any map can be represented by a matrix. Okay, this is very important topic in the linear algebra. In second problem, I am going to give for you 3, 2, 1, 4, 5, 2, 0, 7. That's it. This is also a matrix. You can find a map for it also. Okay. Finally, I am giving a big problem for you. X, Y, Z, W, which is equal to x plus y, comma y plus z, comma w. Okay. Can you derive this one? This is the map. First, you have to find your problem is, first you have to find it is linear transformation or not. Next, you have to verify rank nullity theorem on this map. So, take it as a practice problem and thank you everyone.